So for this problem, we're going to evaluate the definite integral from 1 to 2 of x squared minus x dx. And we're going to use the integral long cut method. For any integral long cut method, we're going to just apply this formula that converts the definite integral to the limit definition of an integral, which is the integral from a to b of f of x dx equals the limit as n approaches infinity of the sum of f of xi delta x, where delta x equals b minus a over n, and xi equals a plus I delta x. So, to solve our formula, we need to first figure out what delta x and xi are. And since delta x equals b minus a over n, we know b is 2, a is 1, so 2 minus 1 over n is equal to 1 over n. So now we have our delta x, and our xi is a plus I delta x. Now, a common mistake is to drop the a. You have to remember to keep the a because it's your lower bound. So if your lower bound is 0, your a doesn't matter. But for a lot of problems, the lower bound of your definite integral is not going to be 0. So if you drop the a, you're going to miss the problem because your xi will be off. So for this problem, our xi is a 1 plus I times 1 over n. So 1 plus I over n is our xi right over here. And now that we know our delta x and our xi, we can start applying our limit definition of an integral now. So the limit as n approaches infinity of delta x, I just pulled delta x out from the summation, 1 over n times the sum of f of xi. And to figure out f of xi, every time we see x, we're just going to plug in xi instead. So when we see x squared, it's going to be 1 plus I over n squared. When we see minus x, it's going to be minus 1 plus I over n. So our f of xi is 1 plus I over n squared minus 1 plus I over n. And from here, we use simple algebra to expand this and then solve it out. And then we end up with the sum of I over n plus I squared over n squared. Now, when we get to this step of the process, it's easier for us to just separate the sum into two summations. So instead of this one sum of I over n plus I squared over n squared, we're going to split it into the sum of I over n plus the sum of I squared over n squared. And it's going to make our life a lot easier. Because from each one of these sums, we can isolate the I by itself. So we're going to pull out 1 over n and then isolate I, and we're going to pull out 1 over n squared and isolate I squared. And once we've done that, we can apply our knowledge of summation rules to know that the sum of I is n times n plus 1 over 2, and the sum of I squared is n times n plus 1 times 2n plus 1 over 6. And then we can multiply that out, and then we fall back to algebra again. It's just algebra all the way till the end until we get the limit as n approaches infinity of just our expression, which is 5n squared plus 6n plus 1 over 6n squared. And we know that the limit as the variable approaches infinity of a function where the highest degree exponent in the numerator and denominator are the same is leading coefficient of the numerator's highest exponent minus over the leading coefficient of the denominator's highest exponent, which in this case is 5 over 6. And you can always check your answer by doing the shortcut or using the fundamental theorem of calculus to check if your answer is correct.